Okay, let's welcome Professor Meng Chen from Fudan University. He is going to talk on algebraic threefolds of the minimal model program. Let's welcome.
Okay, first of all, I would like to thank organizers for the invitation. So this talk is a means to be a brief introduction to explicit high-dimensional birational geometry. So thanks to a very good introduction of Professor Mori. So in dimension 3, so this talk can be regarded as some going on after MMP. Okay, because not everyone is on birational geometry, so this talk is elementary, and I just review some results and methods which are are related to my own interest, not meant to be a complete overview to this area. Okay, so first, so I only consider the complex geometry. So I everything is working on K algebraic closed with of characteristic 0. So for example, K equals to C. So as everyone knows, the target set of birational geometry is we can study this set, which is a set of projective varieties. So we want to classify these. So from the birational geometry, the first step is to study the birational equivalence, which means that these two varieties, they have x and y, they have the same isomorphic uh, uh, yeah, function field as an extension over K. So modulo birational equivalence, then the target set becomes V bar. So that means we have to study each classes as a equivalent class. So V bar, of course, we can divide this according to dimension. Okay, so as Professor Mori explained, when n equals to 1 and 2, so this is the theory is is very satisfactory. Yeah, from the time of Riemann, and due also in dimension 2 case due to Italian the group of the work of Italian group. Okay, so in dimension 3, the minimal model program was established approximately between 1980s to 1990, and of course, we know that MMP, as Professor Mori explained, it works inside the each equivalent class as a subset of V. So roughly saying, suppose this rectangle contains all those objects of a certain given variety, which are all birationally equivalent to each other. Then the MMP, the strategy is just like this, starting from any object, any variety. So the MMP predicts that after a finite number of elementary contraction or deformation, then you will get you arrive at some rate point. This is usually called minimal variety or minimal model. And every any two objects, they are connected, yeah, after some finite steps of elementary deformation. They are connected by minimal models. And for any minimal model, yeah, their relation are also can be described. Yeah, here roughly they are connected by flaws. Yeah. So this strategy or MMP, this theory just says that any two objects inside some single equivalent class, their relation are explicitly described. Okay, so this is what MMP wanted to do. Okay, so in dimension 3, so this theory was established between 1980s to 1990. The main group, yeah, of course, yeah. For example, by Mori, Reid, Kawamata, Shukurov, and Kola, and so on. Okay, of course, there are many mathematicians who did this theory. Starting with a smooth projective threefold weight, you can have a minimal model. So what do you mean by minimal model? So minimal model in algebraic geometry means two meanings. So if the Kodaira dimension is negative, then that means this minimal model is usually referred to as a Mori fiber space. So there is natural fiber structure onto another low-dimensional variety, and with general fiber, pick a number 1 and funnel. Okay, so otherwise, the minimal model means this variety has nav. In algebraic geometry, this means numerically effective, or in some analytic sense, it's that semi-positive or something. Yeah, some semi-positive property, or in other words, the intersection theory, this divisor intersects with any curve being a non-negative number. Okay, so the problem reduced to study the minimal models. Okay, so for due to the minimal model theory, so from this point of view, there are three fundamental types of varieties. So the first type, as everyone knows, is so-called funnel varieties. The second type is those like Calabi, some it's the canonical bundle of canonical divisor Kx numerically equivalent to 0. And the other type is variety of general type. That means the on minimal model, the canonical divisor Kx is nav and big. So here, every minimal model here, Kx doesn't mean to be a line bundle. It's a Q divisor. Okay. Okay, so after MMP, so what to do? So because the target is to want to distinguish two varieties. So after MMP, so one should distinguish different variation class. So the first step is so-called geographic problem. So which means that roughly saying you can we can find finite number of invariants. Then we have some so-called invariant map. We fix dimension. Then the invariant map maps every classes into some point in QM. So for example, the usual biration invariants can be the canonical volume, geometric genus, Euler characteristic, or so on. But how many invariants are used? It depends. Yeah, I mean, from dimension 3, starting from dimension 3, this is more complicated than dimension 1 and dimension 2 case. Okay, for example, in dimension 1, maybe using this strategy, maybe only one, the geometric genus, that the genus is enough. In dimension 2, maybe if we consider a variety of surface of general types, maybe 2 is enough. Maybe C1 square and C2. Okay, so I just explain the idea. So the fundamental question of geography is to you have to determine the image of the invariant map, say tau V3. Okay, so what is the image of this? Suppose you know the image exactly, then the last step could be to ask such a question given any point in the image. So what is a pre-image? The pre-image in algebraic geometry is exactly so-called moduli space. Okay, so suppose we know the geometric property of moduli space, then roughly we can say this classification theory is somehow complete. Of course, this theory is you can see this theory is successful in dimension 1, 2, and in high dimension for many special classes. Recently there are more new advances in this area. So today I only concentrate on dimension 3 case because in dimension 4 and 5 maybe it's still difficult to determine this geography. So I only consider some objects for threefolds. Just maybe only 2 types. Today I will only mention 2 types. One is funnel type, another is general type. Okay. So for threefold, usually the Bayesian invariance. So we use nothing but this. The first is canonical volume. This is if it's minimal, if x is minimal, then it's easy to define canonical volume. Just it's just a self-intersection number. Yeah, this is usually a Russian number, and plurigenus, of course, it's a Bayesian invariant for any positive integer m. You just consider dimension of this group, h naught of m. Okay, and we have other other Bayesian invariants such as irregularities. First irregularity, H1OX. Second irregularity, or geometric genus. Yeah. And finally, maybe Euler Tangle characteristic. Okay, so I first review some results on funnel threefolds. Here, funnel, for what I mean, it's a Q funnel, not a manifold. That means it's a minimal threefold in the sense of Mori. So minus kx is a Q Cartier wave divisor. Okay. So there are some known results. So from the classification, so I want to first I want to record the boundedness. The boundedness, for funnel threefolds was first studied by Kawamata. He first studied the funnel threefold with the pick number 1 case. And Kawamata proved that this is bounded. This is a bounded family. Bounded. And then in 2000, Kola, Mioka, Mori, and Takahashi proved in general case. That means without the restraint on picker number 1 for other picker number. So therefore, yeah, because Q-funnel threefold is bounded, so therefore we can start to study the exact boundedness or or even classification. Okay, so I have to say so the great work of Mori and Mukai. So they use the MMP in dimension 3. They first classified funnel threefold, smooth funnel threefolds in with 87 types. So this is famous list. As also Professor Mori mentioned. And some other classification due to Mori, Prokhorov, and some other many such works for non-Gorenstein or non-smooth case. But it seems that it's very difficult to list, give complete list one by one those types. So we need some new method or some another point of view to do the classification. So for me, I'm interested in some numeric boundedness. Okay, of course, there is one important work, for example, for K-stable funnel inflows. So recently there is a great achievement on this. For example, the work of Chen, Danielson, and Sun, and Professor Tian, and also by the group of Chen Yangxu, they constructed the moduli. So, but for me, in my opinion, so because not every funnel, every Q funnel is equipped with KE metric. Okay, so because not every Q funnel is has KE metric. So we want to find another way to study general some other to treat every funnel. Okay, so I don't mention their work here. So I'm interested in the so-called anti-canonical geometry or So first is the so-called anti-canonical volume. So for a Q funnel threefold X, so we can always because this means minus Kx is Q ample. So therefore the anti-canonical volume here I add a minus here. This being the anti-canonical volume. It's a rational, positive rational number. So because all Q funnel varieties, Q funnel threefolds are bounded, so so it's natural. We should ask what is exact lower bound or upper bound for this quantity. Okay, so actually using threefold, especially using weighted basket theory. So in 2008 with Rong Kai Chen, so we first proved that the anti-canonical volume of Q funnel threefold has the lower bound 1 over 330. So this is the optimal lower bound. I say it's optimal because there is an example. I will mention this. For upper bound of the anti-canonical canonical volume, it has been a long time to achieve this. Before previously, Prokhorov and his group maybe they have some upper bounds, but so far the known optimal upper bound is the upper bound for the Gorenstein case. So that means if you consider Q funnel threefold with minus kx Cartier, then there is the upper bound. Yeah, it's like this. But in general, it has been a long time to know the effective upper bound. But only until recently, it's done by Chen Jiang and Zhou. So and Zhou. So they have they got the upper bound, got an effective upper bound. Okay, but so far this is maybe it's not optimal, but I mean it's the method is quite delicate. It's yeah. Anyway, this is the first effective upper bound. Yeah. Okay. So so on the other hand, we want to we can study anti-canonical geometry. That means we can study such a question. So we define the anti-canonical stability index. That means this is a minimal number n, so that for any integer m larger than n, minus mk, this anti-M canonical system defined birational map. Okay, this is a stable birational map. So given x, this number is fixed, and then I define, because this is a bounded family, so we can define W3 to be the maximal anti-canonical stability index. So W3. So the question is, what is the number W3? Or W3 is upper bounded by what number? So this is a general quantity to describe it yeah, from the point of view of anti-canonical geometry. So in 2016 with Chen Jiang, so we proved that M3 is smaller than or equal to 1997, and again recently it's improved by Chen and Zhou. Zhou was my former PhD student. So they improved this to be to 59. Okay. So it's yeah. So far we only know this upper bound, but it's from the point of view of classification, it's better. We know the exact number W3. So but so far yeah, due to technical reason, it's yeah, seems to be difficult. To work out this number. So here's a conjecture. So the conjecture says it's very easy. Just say W3 is 33. So because we have this example, so just take a general hypersurface of 60 degrees 660 in weighted projective space. So you will find that this is a funnel threefold, and with the anti-canonical stability index is 33. And of course, this volume is the anti-canonical volume is 1 over 330. So this is yeah. So because there is such example, so it's natural to make this conjecture. But so far, this is open. To me, it's a very interesting question. Okay. So on the other hand, I explained for threefolds of general type. For threefolds of general type, this is in contrast to funnel case, because everything in funnel case so the canonical volume is negative. In the general type, this is positive. So it seems to be there in contrast to two pores. Okay, but the methods are quite different. Yeah. So for varieties, for threefolds of general type, so that means for starting from any minimal model, you have a naive and big canonical divisor Kx. Of course, the minimal model has usually Q factorial terminal singularities. And so what we will do is steer some canonical way. For example, pluricanonical map. Yeah, this is defined by the pluricanonical linear system. So this map phi m for any positive integer m, this is intrinsic due to the given threefold. So therefore, it's important to know the geometry of this pluricanonical map. So for example, we can define the canonical stability index. So this is nothing but the minimal positive integer n, so that for any m larger than n, the phi m is birational. So this is a birational invariant. Yeah. So this is invariant. Yeah. For any minimal model. So that means if you have two minimal model x1 and x2, if they are birational equivalent, then this number is unique. This is only determined by the birational class. So this is a birational invariant. Of course, the canonical volume. That means this is the self-intersection of kx cubed. So this is a positive Russian number, and similar to the Q-funnel case, we can study the third canonical stability index R3. So this is the minimal. There's a maximal canonical stability index. So this is a global quantity for threefold for birational geometry in dimension 3. So this is an important number. For example, in curve case, R1 is 3. In surface case, R2 is 5. So how about in dimension 3 case? So in dimension 3, this is much, starting from dimension 3, this becomes quite different with low dimension case. So I will mention this. So actually, Kola and Mori, they set out the problem, open problem in their book. So they ask, so what is the R3 actually? What is the upper bound of R3 or the lower bound of V3? So okay. So Heikon and Makana and Takayama Tsuji, actually they proved in general the Rn. So Rn should be a finite number. So this is the so-called canonical boundedness. Okay, for any dimension. Yeah. So that's why we can say. So why? So if you only define this number, then it could be plus infinity. Yeah. So how do you know this is how do you know this is some certain finite number? So this is first proved by these four authors. So they proved that Rn is some certain number. Okay. So in dimension 3, with Meng Chen, we established some theory of weighted basket. So we solved this question. Here is the result. For any minimal threefold of general type, we know that the lower bound of the canonical volume is 1/1680, and the upper bound of canonical stability index is 57. And actually, for any threefold of general type, we know the 12th 12th genus is positive, and 24 the plural genus is at least 2. So actually, we found some new invariants, say delta x. So actually, a threefold of general type can be divided into 18 classes according to this delta index. And actually, when delta index is larger than 13, then it's completely classified, and we have list for all possible numerical invariants. Okay, but when delta is smaller, delta is between 1 and 12, then we can use an effective way to recover the geometry of the Barash geometry of threefold. So this makes it possible for us to get this lower bound of the canonical volume or upper bound of the canonical stability index. But even though this is very effective, but so far we cannot finish this work because for us it's better we can know this R3. What is the number? What is the value of R3? So for in surface case, this was a famous work of Bombieri. Okay, R2 equals to 5. It's very clear. But in threefold case, this is somehow very complicated and difficult. So far, we hope we can work out this, but seems we still have some difficulty. Okay, so here is a example of Fletcher. Fletcher had such an example. This is the first example shows that in high dimensions, a variety can have very small canonical volume. So this is a general hypersurface in weighted projective space. So this canonical threefold, it has canonical stability index 27, and the canonical volume is 1 over 420. So this is the first very interesting example. But before this, I think maybe even people believe that maybe in high dimension every variety should have integral canonical volume. But in 1980s, so people already know that in high dimensions the canonical volume could be usually could be a very small Rush number. So it's interesting. So what is the minimal canonical volume or the maximal canonical stability index? So actually, this was so-called Haken-Markkanen conjecture. So I think they made this conjecture just due to this example. So that means it's conjectured that the canonical stability index should be 27, and the minimal volume should be 1 over 420. So this is based on this example. But so far, no other examples with any with volume, with canonical volume smaller than this number. So I don't know. So this is still a very interesting problem. Okay. So at last, I want to explain the three-dimensional geography. So this is only until recently it's we really have some new progress on this project. So what does this mean? So the geography for threefold in general, it's we want to define some invariant map from the set of threefold classes to another space. So the point is how many invariants is enough to study the geography and study moduli. So this is a very delicate question. So I think this theory is still in the very early stage. So I just so the first step we just try to understand the relation between two invariants. For example, for me, so from 20 years ago, we started to study the relation between the canonical volume and the geometric genus PG. Okay, so why we are doing only consider this? Yeah, because uh, it seems only possible to study these relations. Yeah, in general, in threefold case, the chi OX is not necessarily a non-negative integer. It can be both negative and positive. So it's harder to detect because this is the volume, canonical volume is a rational, a positive number. So actually we want to recover this relation between canonical volume and geometric genus. So if you know the story for surfaces, the geography of surface, then the famous Noether's inequality was you know that there is in surface case there is some Noether inequality. Okay, in dimension 3, we want to this is a figure we try to work on. So we start a relation between the volume, canonical volume, and the geometric genus. So this strategy says that every minimal threefold general type is distributed above this line, and this line is so-called Noether line. And first of all, it's easy to find examples given, given any value of geometric genus. Then you can have more and more examples with the canonical volume as large as possible. So that means above, in the upper side, on the upper side, there is no upper limit. So that means that every threefold of general type are distributed in this area. But how can we define the lower bound, detect the lower bound? So this is the so-called the Noether inequality. So in threefold case, let me first recall the case for Gorenstein threefold. So people are studying this only when this is a very special case. That means the threefold X has the minimal threefold X has a Gorenstein Cartier canonical divisor is Gorenstein. Kx is Gorenstein. No, the Kx is Cartier divisor. This means Gorenstein minimal threefold. So for Gorenstein case, that this inequality holds. The red color inequality holds. So this was first proved by myself in 2004. So I first proved this inequality for canonically polarized threefold. That means X is smooth and Kx is ample. Okay, and then gradually generalized to general case. For example, with Catanese and Deqi Zhang, we generalize this inequality to smooth and minimal case. And then finally in 2015 with Meng Chen, we proved this inequality for Gorenstein minimal case. But anyway, this inequality was proved only when we assume Kx is Cartier. But this is not this is not a general assumption. For a general minimal threefold should not have Kx Cartier. So For general case, we will I should mention. So the first why we know that this is optimal. Then so first Kobayashi, a Japanese researcher, Kobayashi, he gave a series of examples making this equality holds with infinite number of examples. So then there were some new construction, and but anyway, so all these examples are they were found by doing double covering. Okay, so in general case, that means we only assume x is minimal. That means kx is Q Cartier and kx is infinitely big. Then this inequality was proved only until recently. So so starting from 2007, so I wanted to study when geometric genus is smaller. For example, 2, 3, and 4. So, and then only until 2020, we proved this general case for geometric genus PG larger than equal to 11. And only the last year, we worked out the last case, the open case, the PG between 5 and 10. So now we can say that this inequality holds for every minimal threefold of general type. So actually, our method can work more. So I want to so I want to to look at this picture. Now we have such a picture. So every threefold of general type is distributed in the colored area, and so now we know that this line is completely proved, and actually actually this inequality the black colored here means actually three lines. That means because it's here we take round up, so it depends on whether PG modulo the residue of PG modulo 3 whether it's 0, 1, or 2. So there are 3 lines actually. Okay, so actually there are 3 parallelly 3 lines here, the first, the second, and third. So, but anyway, so now due to our recent work, we know that any threefold, if it's distributed below this line, or it's distributing in a green area, then the structure is clear. Structure clear means we know they are roughly, for example, they are fibered by curves of genus 2. And secondly, we know that it has a double covering structure over onto some either P1 bundle over some surface, or a P2 bundle over some curve. So so then we started actually our work last year. We started to work out some moduli space. So far in this boundary case, we know somehow some moduli space. For example, so far we know there when PG equals to 2, 3, and 4. So we know that the moduli space at these 3 points, so they are all irreducible. The moduli space is reducible, and so we know the dimension of the moduli. Okay, so when geometric genus is larger, This is a work due to yeah, Kaufland. So Kaufland, Hu, and Pignatelli and Zhang. So when geometric genus is larger, they study the moduli of those threefolds scattered on this nodal line. So the result is that when the geometric genus is large, then you will see that the moduli space has more and more irreducible components. Uh, yeah, so the number of irreducible components is linearly related with the geometric genus PG. That means when PG is larger, then the number of irreducible components is larger. So but yeah, their construction are so-called toric bundle method. So because we have proved that any varieties, any threefolds distributed in a green area, so they are actually fibered by 1-2 surfaces. So yeah, so first they proved that all threefolds on the nodal line, then necessarily has some very defined or refined property. So this makes it possible to work out a moduli. So this is, I should say, this is a three-dimensional analog of uh, of the of the result of Horikawa, yeah, in for surfaces. Yeah. Horikawa studied surfaces on the nodal line. Okay, so yeah, so far, so for threefold, it's there are still two cases which are incomplete. So one is here. So the PG equals to 0. This is the most difficult case. So for PG equal to 0, we only know that the lower bound of the canonical volume is over 1 over 1680, but we still don't know whether the minimal volume. What is the minimal volume? And PG equal to 1. We also have some lower bound here, but so far we could not determine the exact lower bound here. So this is still still the project we are doing on presently. And so finally, I think so in higher dimensions, unlike surface case, because a threefold, minimal threefold usually has a very small canonical volume. So therefore, it's necessary. We should find some way to to construct or to work out some examples with very small volume. So this is a necessary step. Otherwise, we could not know really so how threefolds are distributed. So therefore, in higher dimensions, if you want to study the geography, you cannot avoid to find the effective way to find varieties with volume as small as possible. But this is lower bound is because this is bounded. So our side is bounded. So we should find examples. On the other hand, we should have some effective way to determine the lower bound. So so to find examples is very important. Actually, there's some recently we did this. So we have some new method to construct examples. But before this, it's mainly the example was threefold example are mainly due to weighted complete intersections. So this was first started by Reed. For example, Reed gave a famous list of K3 in weighted projective space. And then his student, Fletcher, he studied threefold case and producing several lists of threefolds with small canonical invariants. So recently we going on the story by Reed, but so for the method of Reed is you assume that the complete intersection are they have canonical or terminal singularity. So then you have many examples of minimal threefolds. But if some hypersurface or some have non-canonical singularity, then there's no way to at least you don't have effective way to calculate the birational invariance. So we did the first first try this. So we assume that the hypersurface has at least has only one non-canonical singularity. Then we managed to find an effective way to see whether after a single weighted blow-up, the upstairs, the variety is still minimal and has canonical singularity. Then we found an effective way to find a lot of new minimal threefolds. To our expectation, so this method works out an infinite number of series of new minimal threefolds with codarial dimension 2. We have we found a lot of new with non-general type, right? Minimal threefolds. But I think those examples are important to study in the future. So not only this, but this paper last year so also found many new examples which makes our result optimal. So for example, in threefold case, we have some when the geometric genus is smaller, so we actually we found in each case we almost found all optimal lower bounds. So these are more or less due to our examples and those examples of this Kaufland, Hu, Pignatelli, and Zhang. Okay, so I think for threefold of general type, there are still a lot of work to do. But so far, I think maybe most important thing is to work out this minimal volume. So that is conjecture 1/420 is a minimal volume. So I hope we will finally work out this. But in general, it seems to be very difficult. Because in high dimensions, if you want to find some examples with very small canonical volume, it's not so easy because you have to find some way to do resolution. And finally, you have to work out the birational invariance. So this is more or less what I'm interested in. So forgive me, I didn't mention other results. For example, there are many intensive classification of funnel case, and also for Calabi-Yau threefold, there are a lot of numerous papers. So because I only concentrate on my interest on the threefold general type. So this is what I wanted to talk about. Okay, I stop here. Thank you.
Thank you for the great talk. Is there any question?
Yes, thank you, Professor Chen. Yes, yeah. Could you simply explain that what does explicit means? Yeah. Yes.
Explicit.
Yes.
Explicit for me. Yeah, so it's relative in relative sense. For me, explicit means here in this talk I mentioned two conjectures. For funnel case, for example, funnel case, what is the exact number of upper bound of anti-canonical volume, and what is the upper bound for the anti-canonical stability index? In dimension, for general type, what I mean is the so-called this conjecture of Haken-Makana. They have such a conjecture. So what do so means we want to exactly work out this number. So this is the first step, and second step. Then we should to work out all the moduli. Moduli means the moduli space of a certain given invariance. So what is dimension, and how many irreducible components of the moduli space, and some geometry property of moduli space, so on. Okay, so this is what I mean explicit. So another, in contrast to explicit, there are in invariant geometry, there's another kind of boundedness. So you just say some objects or some varieties, if they satisfy some property, then it's bounded. Just means they can be parameterized by certain variety or scheme. That means that's doable. Explicit means you have to work out exactly the geometry. So this is what I mean. Explicit.
Yes, thank you, Senator.
Other question? Okay, let's thank speaker again.
Thank you.